In this video, we're going to continue from our previous discussion of radians as a measure of angle to see how we can use radians to find the area of a sector of a circle. A sector of a circle is an area bounded by two radii and an arc, or simply, it's a piece of pi. This here is a sector. Now, to help us in our calculations, we need to use a couple of ratios. The first one is that the area of this sector to the area of this whole circle is the same as the ratio of this arc length, the arc that forms the crust of the piece of pi, to the circumference of the whole circle. Again, the area of this piece of pi to the whole circle is the same as the ratio of the length of this arc to the circumference of the whole circle. Now, I'm not offering a proof for that here, but it does seem pretty intuitive. To write that in formal terms, if we let capital A be the area of the sector, lowercase a be the arc length, and r be the radius, then we have this relationship here. The area of the sector divided by the area of the whole circle is equal to the length of the arc divided by the circumference of the whole circle. If we rearrange this equation to solve for the area of the sector, capital A, we get, multiplying both sides by pi r squared, capital A is equal to lowercase a, the arc length, times pi r squared, divided by 2 pi r. If we divide top and bottom by r and by pi, we get that the sector area, capital A, is equal to the arc length times the radius length divided by 2. So that's one formula for finding the area of a sector. If we know the arc length and we know the radius of the circle, we multiply the two of them together, divide by 2, and that gives us the area of the sector, or the piece of pi. Also remember that theta, the measure of an angle in radians, is simply equal to the number of radius lengths that would fit in the arc, or a over r. We can rearrange that by multiplying both sides by r, and we get a is equal to r theta. If we take this equation that we've just derived and replace a with r theta, we can derive a second equation. So the area of the sector is equal to a times r over 2. Replacing the arc length with the radius times theta, we get r theta times r divided by 2, or a is equal to r squared theta over 2, sometimes written as a half r squared theta. So there's a second equation now for finding the area of a sector, useful if we're given different information. In this case, if we have the length of the radius and the measure of the angle, we can plug them into this equation, whereas in this one, if we have the length of the arc and the length of the radius, we would plug them into the first equation we derived. So this is just a summary of those 2 points. The area of a sector is equal to AR over 2, or a half r squared theta, where capital A is the area of the sector, lowercase a is the arc length, r is the radius length, and theta is the sector angle in radians. And this is really important, that theta has to be in radians. If you try plugging an angle in degrees into this, you'll get an incorrect answer. So if you're given theta in degrees, you have to convert it to radians to use the formula. Let's do a couple of examples. Here we're asked to find the area of a sector of a circle that has radius of 8 centimeters if the arc length is 6 centimeters. To draw a picture, we've got a circle with radius length of 8 and an arc length of 6 centimeters. And we want to find the area of this sector here. So we know that r is equal to 8 and a is equal to 6. And we have our equation which states that the area of the sector is equal to the arc length times the radius divided by 2, and we simply plug our numbers in. We get 6 times 8 divided by 2 is equal to 24, and because it's an area, it's going to be centimeters squared. To look at another example, here we're given a radius of 8 centimeters and a sector angle of 30 degrees, and we want to find the area of the sector. So to draw a picture again, we've got a radius of 8, and this angle here is 30 degrees. We want to find the area of that piece of pi. So in this case, r is equal to 8, and theta is equal to 30 degrees. But recall that we said that you can only use the formula if theta is in radians, so we have to change this into radians. And we know that 30 degrees is equal to pi over 6 radians. And if you didn't recall that, remember you could take 30 degrees, multiply it by pi over 180, which is our conversion factor. We have radians in the numerator because we want to get to radians from degrees. And then canceling out, 30 goes into 186 times, so we get pi over 6. So now we've got theta in radians, which means we can use our equation, our formula. So the area of a sector is equal to a half r squared theta. This was the second formula that we derived. So now we simply plug in, r is 8 squared, and theta now is pi over 6. If we multiply all these out, we're going to get 64 pi over 12, which when we reduce to lowest terms is going to be 16 pi over 3. And again, it's an area and we started off in centimeters, so that's centimeters squared. And we can leave it like that because that's an exact answer. So that's an introduction to how you can use radians to find the area of sectors of a circle.